Welcome to the fifth lecture of Complex Analysis series with course code MAT 18R4026 offered by the Department of Mathematics, Kalasilagam Academy of Research and Education. It's block 1, unit 1.1. So as we have ended in our last class defining linear transformations and some examples of linear transformation and some examples which are not linear transformation. Also, I have given one example which is a linear function, but still not a linear transformation. So to resume that topic, we'll again start here. So, there is something called zero transformation. So how it is defined? T is a mapping from vector space V to W, and T of V equal to 0 for all element of small v in capital V. So this is what we call a zero transformation, and it is quite obvious that this transformation mapping will definitely follow the two conditions of linear transformation. So all zero transformation mapping or zero transformation mapping in particular to say is eventually a linear transformation by default. Similarly, we define another transformation called identity transformation, which is defined over here. T from V to V, where V is a vector space over some field F, or for example, you can also take over the field of real number. It doesn't even matter. You can choose any field basically. You can choose complex field over the field complex, or over the field real, or over any arbitrary field. And the identity map is defined like this: T of V equal to V for all V belongs to capital V. So eventually it maps each element into itself basically. That's why it is called identity transform. And anyone can check, or you can also check, that this function also satisfies two conditions of linear transformation, and eventually it becomes a linear transformation too. So these two are default linear transformation, can be defined on any arbitrary given vector space or any between any two, for zero transformation between any two arbitrary vector spaces. So theorem 4.1, let me take the highlighter from here. Okay, this is the spotlight. Theorem 4.1. What it says some properties about linear transformations. So we choose T from V to W as a linear transformation, and U, V are any two elements from the domain space capital V. Then T0 equal to 0. What it says that the zero vector of V always map to a zero vector of W. One thing we must note here, this T0, T of 0 in parenthesis 0, this 0 is the zero vector of V, and the resulting 0, that is T of 0 equal to 0, this 0 where my highlighter is, this 0 is the zero vector of the codomain vector space W. Property number 2, what it says, T of minus B equal to minus T of B. This is quite obvious. T of minus B, this is nothing but T of minus 1 into B, and from the second property we can take the minus 1 outside of T, so minus 1 into T of B, ultimately it will give you minus T of B. And again number 3, what it says, T of U minus B equal to TU minus TB. Again, combining the first and second condition, anyone can prove the property 3 also. And what property 4 says, suppose V is like this: C1 V1 plus C2 V2 plus dot 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 plus Cn Vn. This is called there is something called linear combination. So this V is linear combination of these vectors V1, V2, Vn. Okay, then one can show that T of V will be C1 into T of V1 plus C2 into T of V2 plus dot 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 plus Cn T of Vn. So these 4 properties are very easy to prove and directly follows from the properties of linear transformation. So I would like to put it as your homework. So please try to prove these 4 properties. It's very easy. Just simply follow the definition of linear transformation. So with that, let me move to the next slide. Okay. Here it is. Yeah. Okay. So as we all know that any finite dimensional vector space has basis. And we also know that R3 is a vector space with rank 3 and basis as these 3 unit vectors 1 0 0 0 1 comma 0 0 comma 0 comma 1. Suppose a given mapping or given linear transformation, rather I would say given mapping is defined on these 3 basis points. Okay, like this. The first t1 comma 0 comma 0 maps to 2 comma minus 1 comma 4. T of 0 comma 1 comma 0 maps to 1 comma 5 comma minus 2, and finally this t 0 comma 0 comma 1 maps to 0 comma 3 comma 1. So at the basis points or at the basis, the function is or the linear transformation is known to us. Then the problem is find t at any arbitrary point. It is given like here 2 comma 3 comma minus 2. So instead of this point, you can find out the value at any point, any arbitrary point on the domain space, that is here R3. So I have taken 2 comma 3 comma minus 2. So let me describe how to solve this, how to find value of t at this particular point. So what we note, we can note very easily that this particular given point 2 comma 3 comma minus 2 can be written as 2 into 1 comma 0 comma 0 plus 3 into 0 comma 1 comma 0 minus 2 into 0 comma 0 comma 1. Now, since t is a linear transformation, the property 4 will follow of the previous slide. So using the property 4, what we can write, this t of this given point equal to 2 into t at 1 comma 0 comma 0 plus 3 into t at 0 comma 1 comma 0 minus 2 into t at 0 comma 1 comma 0. Now this 3 at these 3 points, the value of the linear transformation is given to us. So in the next line, I have put it all the given values here. Then simply calculation, a simple calculation is providing us the final answer, which is 7 comma 7 comma 0. So this is how to solve when a given linear transformation is provided at the basis of the domain vector space. Then we can find the value of the linear transformation at any point, any arbitrary point given on the domain space. This is very easy and very important also to understand the structure of a linear transformation. So this is the next and last slide. What it says, this is rather a representation of a given linear transformation. So how it goes? It goes like, suppose A is a given m by n matrix. The function t is defined by t at v equal to av, where a is m by n and obviously v has to be n by n. Sorry, n comma n. So v is a column vector basically, whose dimension is n by 1. So then av is also defined. Then one can show that this t defined in this way is a linear transformation from Rn to Rm. So here I have described how it looks like. Suppose A into V. So this is a matrix of order m by n. So these are the arguments, Aij are the argument, and this V vector, this is basically a column vector of order n by 1. So, and if we multiply these two, what will be the resulting matrix? The resulting matrix will be of m by 1 order. So that is again a column matrix of order m by 1. So the resulting matrix is written over here. This is the matrix. Okay, this L min dot 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 and in the row and m min continuation in the column. So ultimately, what we can see that T is a linear transformation from the vector space Rn to Rm, and this is the matrix representation also sometimes we say. So suppose any given matrix represents basically a linear transformation. From this theorem we can conclude, definitely conclude. And so for example, suppose we are given with a 3 by 2 matrix. So this is nothing but a linear transformation from R2 to R3. One thing we have to remember, suppose the matrix is m by n, then the linear transformation will be from Rn to Rm, not Rm to Rm. So this is we must note while we using this theorem. So with this note, I am ending today's lecture video here, and student, please follow the next lecture video for continuation of this course.